Hey everyone, welcome to this explainer. Look, if you're building out a local AI lab in 2026, you've probably realized by now that the rules of the game, they've completely changed. Right now, we're witnessing this massive, industry-wide battle. On one side, you have the sheer raw speed of traditional consumer graphics cards, and on the other, the massive, unified memory capacity of specialized AI workstations. So today, we're breaking down this desktop-to-data center bridge, and we're going to help you navigate the wild landscape of 2026 local AI hardware.
Okay, let's jump right into it. Here is how we're breaking things down today. We'll start with the local AI hardware dilemma, then look at speed versus memory capacity. After that, we'll cover price trends, and yeah, we have to talk about the RAM apocalypse. Then, bridging software from desktop to data center, optimizing local training workflows, and finally, how to actually choose your AI workstation.
All right, Section 1, the local AI hardware dilemma.
You know, it used to be so simple. You just go out, buy the biggest, most expensive gaming GPU you could find, and call it a day. But, as any senior AI engineer will tell you, when you're migrating workloads from a desktop prototype to a full-scale server rack, you quickly realize that raw speed isn't everything. It's really all about how your system handles memory. Just look at the stark contrast between our two heavyweights here. You've got the NVIDIA DGX Spark, powered by the GB100 chip. This thing boasts a staggering 128 gigabytes of memory, plus an NVLink C2C interconnect moving data internally at 900 gigabytes per second. Absolute monster. But then, you compare that to a custom PC build running the RTX 5090. The 5090 has a much smaller 32 gigabyte capacity, sure, but it hits a blisteringly fast 1.8 terabytes per second of memory bandwidth.
So, what's the secret sauce for these specialized boxes? It's unified memory. See, in a traditional 5090 setup, your CPU and GPU have entirely separate memory pools connected by a PCIe highway. Now, don't get me wrong, an RTX 5090 combined with Windows 11 and Unsloth, that is an incredible, one-stop local personal AI training and learning lab. It's absolutely perfect for insanely fast image diffusion or running smaller models. But try fine-tuning a 120 billion parameter LLM on it, and you're going to instantly hit a catastrophic out-of-memory crash. It just can't fit. Unified memory solves this by pooling the RAM together, letting the CPU and GPU share one massive physical space. This lets you actually load those massive models and completely avoids that OOM headache.
Moving on to Section 2, speed versus memory capacity.
All right, so how does this architectural divide play out when we actually run the numbers? Well, the data brilliantly illustrates the bandwidth bottleneck. Take a look at decode performance on a massive 120 billion parameter model. A DIY build stringing together 3 older RTX 3090s, it absolutely dominates token generation speed, pushing 124 tokens per second simply because of its raw aggregate bandwidth. The Mac Studio M3 Ultra also puts up a really impressive fight at nearly 71 tokens per second, thanks to its 819 gigabytes per second unified bandwidth. And the DGX Spark? Well, because it's restricted by its 273 gigabytes per second memory, it trails at about 38.5 tokens per second. It literally has to make a compromise on pure speed just to fit that massive model into its compact footprint.
But hold on, the story completely flips when we look at prompt processing. In this phase, the DGX Spark actually edges out that massive 3-GPU 3090 build, screaming past 1700 tokens per second. Why the sudden leap? Because the Spark leverages highly efficient FP4 hardware acceleration built directly into its Blackwell GPU architecture. The AMD Strix Halo system has similar memory capacity, sure, but it lacks that highly specialized acceleration, so it lags significantly behind in this specific metric.
Which brings us to Section 3, price trends and the RAM apocalypse.
Okay, so the hardware is mind-blowing, but we have to talk about the budget. Specialized AI desktops are currently facing some intense pricing volatility, and you absolutely need to factor this in. In February 2026, NVIDIA drastically adjusted the MSRP of the DGX Spark Founders Edition to $4,699. Guys, that's a massive 18% spike from its launch price just a few months earlier and a nearly 57% climb from what they announced at CES. No way around it, that hurts.
People in the industry are actually calling this the RAM apocalypse. And yeah, it's as bad as it sounds. Severe worldwide supply constraints on LPDDR5X memory directly drove this cost increase. This sudden shift changes the value proposition entirely for labs and home users. I mean, if you carefully budgeted for a lab full of these last year, your costs just exploded. It's a massive headache that is forcing a lot of developers to completely rethink their desktop hardware strategy. But hey, there is a silver lining here.
There are alternatives within the exact same ecosystem. The Asus Ascent GX10 uses the exact same GB10 Grace Blackwell superchip as the DGX Spark, but, and this is a big but, you can pick up their 1TB version for around $2,760. How? Because Asus opted for a smaller user-upgradable storage drive format. So you get the exact same 128GB unified memory and compute power, but for nearly $2,000 less. It's a phenomenally compelling entry point right now.
All right, Section 4, Software, Desktop to Data Center.
Because let's be real, the silicon is literally only half the battle. If you ask any enterprise developer, they'll tell you the true value of these specialized boxes is the software bridge they create. These systems run NVIDIA's DGX OS, which is an optimized Ubuntu environment that perfectly mirrors the exact software stack used on full-size enterprise servers. By pulling official NVIDIA playbooks straight from GitHub, you can deploy complex, consistent environments instantly. You are quite literally prototyping locally in an environment identical to a massive H100 data center rack. Plus, they have a built-in 200 gigabit Connect X7 networking card, meaning you can physically link these machines together to test out scale-out software setups right on your desk.
Now, I do have to warn you about a few speed bumps. While traditional CUDA-based development environments have, 15 years of standard tooling under their belt, the GB1 chip relies on an underlying ARM64 architecture, not the x86 standard most PC devs are used to. What does that mean for you? It means you're probably going to run into missing precompiled binaries for certain Python libraries, you might have to manually compile tools, and you will definitely have to navigate some unexpected Docker compatibility issues. Just something to keep in mind.
So the big takeaway here? If you just run standard libraries out of the box on these machines, you're basically throwing your money out the window. To actually overcome those hurdles and optimize your inference speed, you absolutely must utilize NVIDIA's TensorRT LLM updates. TensorRT LLM is what unlocks those 5th-generation Tensor cores and that FP4 acceleration we talked about earlier. It's exactly how these small boxes manage to achieve up to 6 times faster prompt processing on massive foundation models.
Section 5. Optimizing local training workflows. Let's actually map this out into a step-by-step guide for bridging your local prototyping lab directly into an enterprise deployment. Step 1. Get the Unsloth framework set up locally. Honestly, it's an absolute game changer for speeding up training workflows. Step 2. Load your massive foundation model entirely into that sweet 128GB unified memory pool. Step 3. Instead of trying to update all the model weights, which takes forever, use LoRa. This lets you train just the thin matrices, drastically saving compute power on your unified memory hardware. Step 4. Keep a close eye on everything using the NVIDIA DGX OS dashboard. You can monitor your workflow, track GPU utilization, and ensure memory coherence. And finally, Step 5. Because your local DGX OS is a perfect match for the server stack, you can effortlessly migrate your validated fine-tuning project straight to a data center cloud cluster without having to refactor a single line of code. It's brilliant.
A quick detour into thermal management, because it really matters with small form factor workstations. The Asus Ascent GX10, because of its minimalist case design, runs a bit warmer during heavy burst phases. We're talking peaking around 87 degrees Celsius on the CPU. Remember, the GB10 chip has a 140-watt TDP, which only leaves about 100 watts for the networking and the ports. The key takeaway? You need to ensure adequate airflow around these units. They run surprisingly warm for sure, but our testing shows they maintain incredibly stable, sustained performance without any thermal throttling.
And finally, Section 6. Choosing your AI workstation.
So let's balance all these technical and economic trade-offs to help you make the exact right call for your setup. If your primary focus is rapid image or video diffusion models, an RTX 5090 running Windows 11 is hands down your perfect personal AI training lab. The raw speed is unmatched. However, if you're a data scientist wrangling massive 100GB plus LLMs, or you absolutely need that software continuity to bridge seamlessly from your desk to enterprise server racks, then a unified memory machine running Linux, like the DGX Spark or that Asus GX10, is 100% the specialized tool you require.
Ultimately, it all really comes down to matching your architecture to your ambition. You have to ask yourself, does your workflow require the seamless continuity and massive memory of a data center sitting on your desk, or do you just need the blistering raw processing speed of consumer graphics? Evaluate your bottlenecks, think about those software bridges, and build your AI strategy from there. Thanks so much for joining me on this explainer, and I will catch you in the next one.